The answer to that question does not just explain the size of an apple. It whispers the reason the cosmos exists at all. It hints at why there is something instead of nothing, and it suggests that our place here, on this pale blue dot, gazing at the stars, is not an accident, but a consequence written into the first trillionth of a second of time. But to understand that, we must first perform a dissection, not with a knife, but with the mind. We must peel back the skin of this apple, layer by layer. If you could see its true structure, you would gasp. You would see a ghost, a cloud of frenzied, buzzing points of light atoms, separated by distances so vast compared to their own size that it would make the solar system look crowded. There are roughly 100 million cells in this apple. Inside them, roughly 10 million atoms. That's a 1, followed by 25 zeros. 10 trillion individual specks of something we call matter. Each atom is a cosmos in itself, a dense, furious nucleus surrounded by a haze of probability, where electrons exist not as dots, but as waves of maybe. And between that nucleus and its electron haze, a void. If the nucleus were a pea in the center of a football stadium, the electrons would be moths flitting somewhere in the outer stands. The rest is vacuum, so the apple in your hand, the solid weight you feel, that is the electromagnetic force, the sheer, stubborn will of negative and positive charges repelling each other, creating the illusion of solidity. You are not touching the apple. You are feeling a field of force, a whisper from the quantum world saying, "You shall not pass, but we must pass. We must go smaller. Let's shrink ourselves." Imagine we are the size of an atom, standing on the surface of one of the apple's sugar molecules. The world around us is no longer a red, curved surface. It is a labyrinth, a towering, chaotic landscape of molecular peaks and valleys, trembling with a heat vibration that is the very pulse of thermal energy. It is a city of insane geometry, and we are smaller than its bricks. We keep shrinking. The atom we stand near becomes a solar system, the nucleus, a distant, brilliant sun. We are lost in the gulf between. This is the atomic scale, where the rules are set by quantum mechanics, a realm of probability, wave functions, and spooky connections. Here, things can be in two places at once. Here, particles tunnel through barriers they shouldn't. Here, reality is a dice game, and it is still colossally large compared to where we need to go. We shrink further. The nucleus grows from a distant sun to a looming planet. It is made of protons and neutrons, packed together with a force so titanic it defies comprehension. This is the strong nuclear force, the glue of creation. It is 100 times stronger than the electromagnetic force that holds you and the apple together. If you could taste this force, it would be the primal scream of the universe, binding itself into existence. And inside those protons and neutrons, deeper we go into a storm. This is the realm of quarks and gluons, particles that can never be alone. They are prisoners of the strong force. Try to pull two quarks apart, and the energy you pour into the effort spontaneously creates new quarks from the vacuum, binding them anew. It is a world of perpetual, violent marriage. There is no divorce at this scale. We are now 1,000,000 billion times smaller than the apple. The world is a chaos of fundamental forces, but we are not at the bottom, not even close. We must go to a place where the very concepts of place and where begin to melt. We must journey to the shore of reality itself, to the Planck scale, the Planck length, a number so small it is a philosophical argument. 1.6 × 10 to 35 meters. How small is that? Let me try. Take an atom. Now magnify it until it is the size of the observable universe. Stretch it across 93 billion light-years. On that scale, a Planck length would be the height of a single tree. On a planet the size of an atom, blown up to fill the entire cosmos, we are about to cross a boundary. Below the Planck scale, our physics, our Einstein, our Heisenberg, our very mathematics breaks down. It ceases to have meaning. This is the edge of the map. Beyond here, there be dragons. What exists here, we don't know. We can only speculate. With equations that bleed paradox. This is the realm of quantum foam. Forget smooth space and orderly time. Imagine the fabric of space-time itself as a boiling sea, a chaotic, frothing frenzy of virtual particles popping in and out of existence, borrowing energy from the void in a quantum sleight of hand. Tiny wormholes, Einstein-Rosen, bridges forming and pinching off in spans of time so short they are less than moments. They are fractures in reality, stitches in the cosmic quilt coming loose. Here, gravity, which is so weak it can't hold a magnet to your fridge, becomes a quantum force. It writhes and fluctuates with the others. Space and time are no longer a stage. They are actors, tangled, twisted, and probabilistic. This is the foundation, the bedrock, the smallest possible anything to fit inside our apple. At this scale, you could pack Planck volumes, a number so vast it has more digits than there are particles in the universe. The apple contains, in potential, a combinatorial infinity of these quantum foam bubbles. And it is from this seething, meaningless chaos that everything, the quarks, the atoms, the apple, the stars, must somehow arise. So we have reached the bottom, the basement of being. It is a place of pure, untamed potential, a place where why is a meaningless question. Now we must climb. We must take this chaos and build a cosmos from it. We must find the thread that leads from the frothing nothingness of the Planck scale to the crisp, ordered structure of an atom. How does that happen? What are the rules that herd the quantum chaos into particles and particles into matter? The first step is a force, the weakest of all the forces, over short distances. Yet, in its weakness lies a peculiar universe-shaping power. The weak nuclear force it doesn't build, it transforms. It is the alchemist of the quantum world. It allows a quark to change its flavor, a down quark into an up quark. This simple act is the first step in the chain of creation. It is what makes nuclear fusion in the sun possible. It is what made the hydrogen in the early universe begin to cook into helium, and eventually into the carbon that makes up this apple and you. But at the Planck scale, even the weak force is not distinct. Here, physicists believe in a flash of energy so intense it is a number. The Planck energy, the four forces of nature were one, a single, unified, perfect force, a symmetry. Then something happened. The universe cooled, expanded, and in that cooling, that symmetry broke like water, freezing into ice crystals. The perfect unity shattered. The single force fractured into the four we know: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. This was the first and most important phase transition in cosmic history. It wrote the rules of the game. It determined the strengths of the forces, the masses of the particles, and it left behind a question that haunts every physicist alive today. Why these rules? Why these numbers? Why is the strength of gravity 10 times weaker than the electromagnetic force? If it were slightly stronger, stars would burn out in millions of years, not billions, snuffing out the chance for life. If the strong force were a fraction weaker, protons wouldn't bind, and no elements beyond hydrogen would exist. There would be no apples, no planets, no physicists to ask the question. The constants of nature, the speed of light, the charge of an electron, the strength of gravity, they are the knobs on the universe's control panel, and they are set to values that allow for this, for complexity, for chemistry, for life. It appears fine-tuned. Someone tune it. Or is this just one universe in a near-infinite multiverse? A bubble in a froth of cosmoses, each with random constants. And we simply live in the one where the numbers allowed us to be here to notice the anthropic principle. It feels like a cop-out, a metaphysical shrug. But the apple doesn't shrug. It exists. It is proof that the numbers do work. That from the quantum foam, a path was found. The forces broke symmetry, took on their identities, and began to build. The strong force corralled quarks into protons and neutrons. The electromagnetic force gave us light and held electrons in clouds. The weak force allowed them to change and decay, driving the engine of stellar evolution and gravity. Patient, relentless, whisper-weak, gravity waited. Its time would come. They built an atom, and here at the atomic scale, we find another mystery. Why is an atom so big? Why is the distance from the nucleus to the electron so vast compared to the size of the nucleus itself? Why isn't everything just a dense, uniform lump? The answer, again, is quantum mechanics. The electron is not a particle orbiting like a planet. It is a wave of probability, a standing wave around the nucleus, like a note held on a guitar string. And just as a guitar string can only vibrate in certain harmonics, the electron wave can only exist in certain discrete states. It has a minimum energy, a ground state. It cannot crash into the nucleus. It is forbidden by the very laws of reality from getting any smaller. This minimum size is the Bohr radius. It is the basic unit of the chemical world. It sets the size of all atoms, and it is determined by a battle. The attraction of the electron negative to the proton positive is balanced against the quantum mechanical requirement that the electron must have a certain minimum space for its wave function. This is the first major construction project of the cosmos, creating stable-sized atoms out of the featureless soup of particles. It is where the universe went from a boring, uniform plasma to a system with architecture, with chemistry, and chemistry is everything. From these atoms, locked in their specific sizes by quantum law, molecules can form. Carbon can chain into sugars, into cellulose, into the very flesh of this apple. Oxygen can bind with hydrogen to make water, the solvent of life. The electromagnetic force, operating within the quantum playground, weaves atoms together into the dazzling complexity of organic molecules. We are climbing from quantum foam to forces to particles to atoms. We are building the apple from the bottom up, but we are still inside a single cell wall. A universe of complexity awaits us at the scale of life itself, a place where the simple laws of physics give rise to phenomena so complex we have new words for them: metabolism, reproduction, consciousness. How does that happen? How does the blind, mechanical churning of atoms and forces cross the gap into something that lives, that wants end? Remember, we are only halfway down. We've only traveled 31 orders of magnitude from the apple to the Planck length. We have another 31 orders of magnitude to climb upwards from the apple to the edge of the cosmos. What awaits us there? Giants that make atoms look like the Planck scale, voids so large they contain nothing but the fading echo of the Big Bang. The apple is the center. We have seen the below. Now we must confront the abyss above. But before we ascend, we must understand the bridge, the link between the quantum and the classical. The moment when probability collapses into certainty, when buzzing atoms become a solid red skin. What is that boundary? Where does quantum weirdness end and common sense begin? And more chillingly, what if it doesn't end at all? What if the quantum strangeness is always there, underlying everything, and the solid apple in your hand is the real illusion? We'll need to talk about a cat, a very famous, very unfortunate cat in a box, and a man named Hugh Everett, who had an idea so radical it suggests that every time you take a bite of this apple, the universe splits in two. But that is for the next chapter. For now, hold the apple. Look at it. Know that you are holding the midpoint of all possible reality. A nexus, a crossroads. You are holding the silent answer to a question we are only just learning how to ask. The journey downwards has shown us the terrifying, beautiful chaos from which all form emerges. The journey upwards will show us the terrifying, beautiful emptiness into which all form will eventually dissolve. The apple is the balance, the moment of now, the fragile, improbable place where all the forces are in conversation. This is not a philosophical puzzle, it is a physical one. And the answer, or the lack of one, determines the very nature of our reality. It asks, is the universe fundamentally fuzzy, only crystallizing into solidity when observed by a conscious mind? Or is there a mechanism hidden in the math that washes the quantum weirdness away as things get bigger, creating the classical world automatically? The fate of the cat and the meaning of the apple in your hand hangs in the balance. To find the bridge, we must first understand the cement that holds it together. That cement is a phenomenon so common, so utterly mundane, that we never think about it. It is the reason walls are solid, the reason you don't fall through your chair, the reason the apple has a skin. It's called dicoherence. Imagine you have a single quantum particle, like an electron. It can be in a superposition, doing two things at once. Now, put that electron inside something, a molecule, an atom in the apple's skin. What happens? The electron is no longer alone. It is surrounded by a storm of other particles, all vibrating, all interacting through electric fields and collisions. These are its environment, and this environment is a relentless gossip. Every jostle, every photon of heat bouncing off it, every weak electromagnetic tug is a form of measurement, the superposition, that delicate, ghostly state of both, and is incredibly fragile. It's like trying to whisper a secret in the middle of a hurricane. The chaotic noise of the environment instantly reads the system. It copies information about the particle's state out into the world. Is the electron here or there? The surrounding atoms quickly find out, and that information spreads at the speed of light through their interactions. In that Instaca timescale so short it's almost zero for any object large enough to see the superposition is destroyed. It decoheres. The quantum probabilities don't vanish, but they become classical probabilities. Instead of the electron being both here and there, it's either here or there, with a certain chance for each. The and becomes an or. This is the first plank in our bridge. Dicoherence explains why we don't see quantum superpositions in everyday life. The apple is constantly being measured by the air molecules hitting it, by the infrared radiation it's emitting, by the light bouncing off it, by the very atomic vibrations within it. Its quantum states are being continuously broadcast to the universe. It has no privacy. Therefore, it has no superposition. It is forced to be definite. So problem solved? Not quite. Decoherence tells us how quantum weirdness gets washed away. It doesn't tell us which of the many possible definite states the apple actually ends up in. In the equations, after decoherence, you don't get one apple. You get a multitude of apples, all slightly different, each corresponding to one possible outcome of all those quantum events. They are all real in a mathematical sense, but they no longer interfere with each other. They've branched off. This leads us to the first terrifying and magnificent possible answer to the measurement problem. The Many Worlds Interpretation by Hugh Everett in 1957. It is breathtaking in its simplicity and its staggering implications. Everett said, "The wave function never collapses, ever. Instead, every time a quantum system faces a choice decay or not decay, spin up or spin down, electron here or there, the universe splits. It forks into multiple, equally real branches. In one branch, the Geiger counter clicks. In another, it doesn't. Both branches are real. Both cats are real. One alive, one dead, but they are now in separate, non-communicating universes." In this view, decoherence isn't the process of choosing one reality. It's the process of separating realities. The apple in your hand is the apple in this branch, but at this very moment, an unfathomable number of near-identical branches are splitting off from you versions, where a single atom in the apple vibrated differently, where a photon reflected off it at a slightly different angle. You are not just holding an apple, you are holding your apple, the one that belongs to this specific thread of the endlessly branching tapestry of reality. This idea is either the most profound insight into cosmology ever conceived, or a ludicrous fantasy. It solves the measurement problem by eliminating the need for a collapse, but it demands we accept a reality of near infinite copies, a multiverse so vast it makes our observable cosmos look like a speck of dust, and it places a bizarre new significance on the scale of the apple of us, because in many worlds, what separates the branches, information, the specific classical arrangement of atoms that makes this apple, and not another one from a different branch. We, as complex, classical systems made of trillions of Descartes atoms, are the physical embodiment of a specific history of quantum outcomes. We are the story this particular branch is telling. The apple is no longer just a midpoint in scale. It is a monument to a particular path taken through the quantum maze, But many worlds is not the only answer. There are other, darker bridges. What if the collapse is real? What if there is a fundamental physical process that destroys superpositions and picks a single outcome? This is the path of objective collapse theories. These theories posit that the Schrödinger equation, the law that governs the smooth, deterministic evolution of wave functions, is incomplete. It needs an extra term, a tiny universal source of noise that becomes significant for large objects. When a system reaches a certain size or mass, this noise spontaneously collapses its wave function, picking a reality at random. The most famous of these is the GRW theory, Garrody-Riemann-Weber. In GRW, every particle has a tiny but non-zero chance per second to spontaneously localize, to have its wave function suddenly peak at a specific point in space. For a single electron, this chance is so small it would only happen once every 100 million years. It's negligible. But an apple contains about 10 million atoms. That's a lot of particles. The chance that at least one of them undergoes a spontaneous collapse is enormous. And because the particles are entangled linked by their interactions, the collapse of one triggers the collapse of them all. In an instant, the entire apple's fuzzy quantum state snaps into a definite configuration. In this view, the bridge is made of random, microscopic events that amplify into classical certainty. The apple is definite because it's too big not to be constantly collapsing. Its solidity is maintained by a continuous, subatomic pinprick of randomness. This is a profoundly different picture. It says quantum mechanics breaks down at large scales. There is a fundamental shift in the laws of physics between the small and the large. The apple and the electron obey subtly different rules. And then there is the most controversial bridge of all, the one that puts you, the observer, at the center of everything. The Copenhagen interpretation. This was the original pragmatic view championed by Niels Bohr and Werner Heisenberg. It draws a sharp, subjective line between the quantum system and the classical measuring apparatus. It essentially says, don't ask what's happening before you look. The job of science is to predict the outcomes of measurements. The wave function isn't a physical thing. It's a mathematical tool for calculating probabilities. The collapse isn't a physical process. It's an update in our knowledge. But this has a disturbing implication. What qualifies as a classical measuring apparatus, a Geiger counter, a computer, a cat, a human eye? At what point in the chain does the probability become actuality? The most radical extension of this idea is that it requires consciousness, that the final collapse only happens when the information enters a conscious mind, that the universe exists in a haze of potential until it is observed by a sentient being. This is the if a tree falls in the forest question, weaponized by quantum physics. If no one is looking at the moon, does it exist in a definite state? Is the apple only truly an apple when you perceive it to be so? This idea is anathema to most physicists. It seems mystical, putting mind before matter, but it's most eloquent. Modern proponent, the Nobel laureate Eugene Wigner, argued seriously for it. He imagined a friend in the room with Schrödinger's cat. When Wigner's friend opens the box, does his consciousness collapse the system for himself, leaving Wigner outside the room, still dealing with a superposition of friend, who, saw, dead, cat, and friend, who, saw, live, cat. Where does it end? It ends, Wigner suggested, with your own irreducible consciousness. You are the ultimate measuring device, the final cause. So, we have our candidate bridges, many worlds, we walk all bridges at once, in different universes. Objective collapse, the bridge automatically solidifies under the weight of too many particles. Consciousness collapse. The bridge is built by the act of crossing it by observation. Which one is real? We don't know. This is the shocking truth at the heart of modern physics. We have the most successful, most precise theory in human history, quantum mechanics, and we do not know what it means. We don't know what is really happening. All we have are the signs at the foot of the bridge, and experiments are beginning to probe where the bridge might start. For decades, the quantum world was the world of the extremely small and extremely cold, isolated photons, electrons in vacuum chambers, atoms chilled to near absolute zero to quiet the environmental gossip of DECOHERENCE. But in the last 20 years, we've begun pushing the boundary. We've created superpositions with larger and larger objects. We've put molecules composed of 2,000 atoms into a superposition of 2 vibrational states. We've sent a virus-sized drum made of billions of atoms into a quantum vibration, where it is simultaneously moving and not moving. In 2021, a team in Vienna demonstrated quantum superposition in a molecule of tetraphenyl porphyrin, a lacy, complex organic molecule so large it is visible under an electron microscope. It was in 2 places at once. The bridge, it seems, is much longer than we thought. The quantum classical boundary is not at the size of a cat. It's somewhere out there, in a misty realm between a large molecule and a grain of sand. The apple is deep into the classical realm, but the foothills of quantum weirdness extend further into our world than we ever dreamed. This brings us back, with new eyes, to the apple. Look at its red skin. That color is not a solid, intrinsic property. It is a story of collapse. White sunlight, a mixture of all colors, hits the skin. Molecules in the skin absorb most wavelengths through the quantum interactions of their electrons. But the wavelength we see as red that is reflected, it is the wavelength the apple's molecules rejected. Every photon of that red light hitting your eye was once part of a probability cloud. The act of reflection was a quantum event. The act of hitting your retina and being converted into an electrical signal was a cascade of quantum chemistry. Your brain's interpretation, the perception of red, is the final link in a chain of events that began with a superposit, the apple's solidity, its texture, its very existence. As a single, coherent object, all of it is a consensus reached by trillions upon trillions of decohering quantum events, happening femtosecond by femtosecond, holding the line against the underlying chaos. The apple is a miracle of stability, a riot of quantum probability, tamed and orchestrated into a silent, edible symphony. And you are made of the same stuff. Your senses are not passive windows. They are active participants in this grand process of collapse, or branching, or decoherence. When you touch the apple, you are not just feeling electromagnetic repulsion. You are engaging in a fundamental physical process that defines the nature of reality at the human scale. You are the bridge walker. But our journey is only 1/3 complete. We have descended from the apple to the plonk abyss. We have now crossed the bridge of certainty from the quantum to the classical, to stand firmly on the apple itself. Now, we must use the apple as a launch pad. We must look up if the journey downward was into a maelstrom of infinite smallness. The journey upward is into a void of infinite largeness. And the first step out of the apple's world takes us into a realm governed not by the fierce, intimate forces of the quantum, but by a patient, pervasive, and ultimately dominant power. Gravity. We have been living in a bubble. The scale of life, of chemistry, of apples and people, is a bubble where electromagnetism reigns supreme. It binds atoms, powers nerves, paints sunsets. It is the force of complexity. But step beyond this bubble, and the universe changes character. Dramatically imagine our apple floating in space. Now, imagine it begins to grow, not by adding atoms, but by us shrinking our perspective. Let it become the size of a car, a house, a mountain. As it grows, something subtle shifts. The electromagnetic forces holding its atoms together remain just as strong. But a new force, negligible at the human scale, begins to awaken. The gravitational attraction between all the mass in the apple starts to add up. It's the faintest whisper, starting to pull the apple's material inward. It grow to the size of a small moon. Now gravity's whisper becomes a command. The rock and ice of the apple's material are not strong enough to resist their own mutual attraction. The apple, if it were made of real apple material, would begin to deform. Its irregular shape would be pulled relentlessly into a sphere. It would undergo gravitational collapse until the electromagnetic repulsion of its atoms, the same force that makes it solid in your hand, finally pushes back, creating a new equilibrium, a spherical body. This is the threshold, the point where gravity graduates from a background curiosity to a asterisk architectural force. Keep going. Let the apple swell to the size of the earth. Now, gravity is the master. It holds the atmosphere against the vacuum of space. It shapes the planet into a near-perfect sphere. It creates pressures at the core so intense they melt iron, the apple's delicate cellular structure. Its sugars and membranes would have been utterly annihilated long ago, crushed and transmuted into minerals. The forces that define the chemical bonds, the cellular walls are irrelevant at this scale. They are overruled. Now, the gravitational pressure at the core becomes so astronomical that it overcomes the last line of defense. The electromagnetic repulsion between atomic nuclei. Atoms are smashed together. Their electrons are stripped away, creating a plasma, seething soup of nuclei and free electrons. And then the nuclei themselves are forced so close that the asterisk strong nuclear force, the glue of the atomic nucleus, which we met in the deepest quantum depths, reaches out and grabs them. Nuclear fusion ignites. The apple is no longer an apple. It is a sun, a titanic furnace where the ancient alchemy of the universe is performed. Hydrogen fuses into helium, releasing the binding energy that once held it apart. This energy, streaming outward as radiation, creates a pressure that pushes back against the crushing weight of gravity. A star is born, and it exists in a precarious, violent balance. The inward crush of gravity versus the outward rage of nuclear fire. This balance point, this knife's edge, determines the size of the star asterisk. It is the cosmic analog to the quantum balance that determined the size of an atom. And here we find our next confluence, our next apple-scale moment in the cosmos. Stars are not random sizes. They occupy a specific range, too small below. About 8% the mass of our Sun, and gravity can't muster enough pressure to ignite sustained fusion. You get a failed star brown dwarf, too large above about 150 to 300 solar masses, and the radiation pressure from the furious fusion is so intense it blows the star apart, stripping its outer layers away. Stars, like apples, have a Goldilocks zone, and our Sun is, once again, remarkably near the middle of that range. A typical, unremarkable G-type main sequence star. Why? Why this range? Because the fundamental constants, the strength of gravity, the strength of the strong force, are set to the values they are. Change them slightly, and the range of possible stellar sizes shifts or vanishes entirely. No stars, no heavy elements, no planets, no apples. The apple scale of the human world finds an echo in the stellar scale of the cosmic world. Both are balance points. Both are places where multiple forces are in tense, productive equilibrium. But gravity is just getting started. It has grander, darker designs. What happens when the star's nuclear fuel runs out? The fire dies. The outward pressure vanishes, and gravity wins. What happens next depends on the mass of the corpse. For a star like our Sun, gravity collapses it down until the quantum pressure of electrons, the same Pauli exclusion principle that gives atoms their size, pushes back. You get a white dwarf, an Earth-sized object with the mass of a star. So dense, a sugar cube of its material would weigh as much as an elephant. For more massive stars, even electron pressure fails. Gravity crushes the electrons into the protons, turning them into neutrons. The entire star becomes a giant atomic nucleus, a neutron star. A object the size of a city, but with the mass of a mountain range spun up to dizzying speeds, with magnetic fields that could erase a credit card from 100,000 miles away. And for the most massive stars, nothing in the universe can stand in gravity's way. It collapses forever. Space-time itself, a black hole, is born. Here, at the end point of stellar evolution, gravity achieves its ultimate, purest form. It creates a singularity, a point of infinite density, where the laws of physics, once again, break down. It is the Planck scale's dark twin. One is the frontier of the infinitely small, born of quantum chaos. The other is the frontier of the infinitely dense, born of gravitational triumph. And between these two infinities, the quantum foam and the gravitational singularities, sits the entire ordered universe of stars, planets, and apples. But we are not done climbing a single star. Even a black hole is not the largest structure gravity can build. Gravity is patient. Over billions of years, it works on a canvas of almost nothingness. It gathers stars into galaxies. It gathers galaxies into clusters, and clusters into superclusters. It weaves the cosmic web, the largest pattern in nature, a filamentary lace of galaxies surrounding voids of breathtaking emptiness. We are about to leave the realm of objects and enter the realm of structure, the architecture of emptiness itself, and at this scale, a new mystery awaits. A mystery that was discovered in 1998 and which has shaken cosmology to its core. It is the reason our universe's story will not end in a fiery collapse back into a singularity, but in a slow, cold, and lonely dissipation. It is called dark energy, and its discovery means that the universe is not just expanding, it is accelerating. Something is actively, relentlessly pushing space itself apart. What is it? We have no idea. It is the greatest unsolved problem in all of science. But it sets the final scale, the ultimate horizon, the largest thing we can ever possibly see, the observable universe. This sphere, 93 billion light-years in diameter, is not the whole universe. It is just the part of it from which light has had time to reach us since the Big Bang. It is our island in the cosmic ocean, the ultimate apple of our perception, and its size, its very existence, is determined by a three-way battle. The initial explosive energy of the Big Bang, the pulling force of all matter and dark matter, gravity, and the pushing force of dark energy. We are inside that bubble, living on the skin of an apple, at the precise midpoint of all possible scales, in a universe balanced between three unknowable titans: quantum chaos, gravitational collapse, and dark energy's repulsion. How did we get here? Why is this balance so perfect that it allows for apples, for stars, for galaxies, for us? The answer, perhaps, was written in the first infinitesimal moment, in a period of unbelievable exponential expansion called inflation. But that is a story for the next chapter. For now, consider this. We have crossed the bridge of certainty. We have seen how the quantum becomes the classical. We have felt gravity awaken and take command of the cosmos. We stand now, with the apple in hand, at the foot of a much larger climb. Ahead lies the stellar forge, the galactic whirlpool, the cosmic web, and the dark energy void. The apple was our starting point, our center. It is about to become our spaceship in our next chapter. We ignite the furnace. We will ride a beam of light from the apple's skin to the heart of a star. We will witness the birth of elements in supernova explosions. We will feel the space-time around a black hole twist and scream. And we will ask, are we, who are made of stardust, just the universe's way of looking back at itself? Or are we something else entirely? The climb to the stars begins now. The apple is in your hand. Don't let go. The universe is waiting to show you how small you are and how significant